Okay, so the entire unit review in, we'll see how many minutes this takes. MVT, the conclusion was calculus slope equals algebra slope. The condition was if f is continuous and differentiable. Differentiable. If f is continuous and differentiable. And this is where they like to sneak in that you need to know that differentiability implies continuity. A lot of times they tell you it's differentiable, and that means it's continuous, but you have to say that. If you want to use MVT, you have to say f is continuous and differentiable. Therefore, so here's the then. This is where calculus slope equals algebra slope. And we wrote this 3 or 4 different ways because people's brains kind of work differently and lock on to different things. IROC equals AROC, that's the same thing. F prime equals M. So now we're getting into like abbreviations, but if you know what those abbreviations mean, F prime, that's calculus. M, that's old school algebra slope. And however you want to phrase that, somewhere on the interval. On a given interval, I guess I should say. And usually the question is, where on the interval does it work? Like, where can I find, or where is the calculus slope equal to the algebra slope? All right, that's MVT. It's been a while since we MVT'd, so let's do an example problem with MVT. We're not going to jump back and forth on all of these topics because it would take too long, but MVT has been a while. So grab worksheet 5, and we'll do 1 and 2 to refresh our minds on MVT. So we'll go back and forth a little bit between our review page and our review worksheet. So it should be in that same packet you were just graphing on, yes. Number 1, let f of x equal 2x plus 1 over x. What values of c are guaranteed by the mean value theorem on the interval (-1/2 to 1). And I like that it's a multiple choice question because we see that last answer, and it's like, okay, well, I need to consider the fact that maybe this doesn't even work, which makes me think I've got to worry about the conditions before I worry about calc slope equals algebra slope. My guess is if I set calculus slope equals algebra slope, I get one of these answers. The trouble is, let's worry about conditions. Continuous and differentiable on this interval, (-1/2 to 1). All right, well, is it continuous and differentiable on that interval? Look at the function. And there's something that should be sticking out at you. Yeah, there's an x in the denominator. So what does that mean at x equals 0? It's undefined. Yeah, and we could get more specific. I think it's an asymptote, but I don't even need to get that specific. At x equals 0, f of x is undefined because we can't divide by 0. Again, in pre-cal and in other places in calculus, we might want to know exactly what's going on there, but for this, that's enough. It's not defined at 0, so it's not continuous at 0, and 0 is on the interval, so we don't meet the conditions for MVT.
You have to write all of that on a multiple choice?
So on a multiple choice, no, definitely not. You would just circle D and move on. On a free response, I guess there would be 2 dangers of the free response. One, if without that answer there, are you going to be sure to check for that? And 2, you would need to show some of that stuff in there so that I know what you were looking at and why you're going to say MVT doesn't apply.
What's the thing about the open interval and closed interval?
that is rarely tested. It's continuous on the closed and differentiable on the open. Which is to say, if it's very rare that one of these would be true and not the other. So you really usually don't have to worry about that. Obviously, on a multiple choice test, you don't have to worry about that. Okay, so number 1 was an easy one if we knew what we were looking for.
Just making sure that's just because 0 is in between -1/2 and 1/2.
Yes. As opposed to, like, what's the rest of your question, I guess?
Like if it was from 1 to 2.
Okay. If we had a different interval, then 0, if 0 wasn't on the interval, then we could use MVT.
Yeah.
All right. Without peeking ahead, Justin knew, look at number 2. Same formula, same question, different interval. This time our interval does not include 0, so we're good. So I can throw D out. There's going to be an answer for number 2. And in fact, I can throw out one of the other answers right away. I can throw out 2 of the answers right away. Why are you throwing out 0? Yeah, well, a couple things. It's not on the interval, and it's undefined. So multiple reasons can't be 0. That's not even the one I was looking at. Why can I throw out A? Because the negative one isn't even on the interval. So, well, that was an easy question. But let's actually work this one to make sure that B is correct. Because, I mean, you wouldn't have to on the test. Like, if that happened, then great. Like, it's got to be B, move on. You don't even have to worry about it. But for an open-ended question, a free response question, we would say that G is continuous and differentiable on that interval. Actually, I guess we'd have to separate this. Continuous on the closed, differentiable on the open. So MVT applies. F prime equals M. That's like the shortest way to say it, but that doesn't have any concepts behind it. So I usually say calc slope equals algebra slope. F prime would be, let's see, that's 2x plus x to the negative 1. I'm rewriting that so I can take a derivative a little easier. 2 minus 1x to the negative 2. And then to get the algebra slope, I'll need to do algebra things, so I'll plug in 1/2, and I'll plug in 1. So I plug in 1/2, that would be 1 plus 1 divided by 1/2. But 1 divided by 1/2 is 2, and then the plus 1 is 3. And then if I plug in 1, I get 2 plus 1 is 3. Oh, that was kind of them. So the slope, the algebra slope, 3 minus 3 over, and then it doesn't really matter what the bottom is because you've got a 0 in the top. 1 minus 1/2. So 2 minus 1 over x squared equals 0. So that means 2 equals 1 over x squared. Trying to move things around here. Multiply by x squared, divide by 2. Take the square root of both sides. That's where that plus or minus comes from. So if you just work the problem without thinking, without really thinking about it, you might have picked A, because you do get both those answers. But the negative one is not on the interval, so only positive square root of 1/2. MVT, calc slope equals algebra slope, as long as the original function is continuous and differentiable, and your answers have to be on the interval. All right, back to the review page here. Next, we did a whole bunch of stuff with the first derivative, and a whole bunch of stuff with the second derivative. And there was sort of parallel stuff. So on this, I'm going to try to write these out. I'm going to fit it all across the line here for f prime, and then I'm going to put the same type information right underneath that for f double prime. All right, we would take a derivative and set it equal to 0, or undefined. See where it's undefined. And do you remember what the name of those points are called? Those are critical points. So f prime equals 0 or undefined. Those give us the critical points. Sometimes we ask for the critical points and you're done. What usually comes next, though? What do we do with the critical points? If we want to find increasing and decreasing intervals and maximums and minimums, put them on a number line. And that leads to increasing and decreasing intervals. Put them on a number line. We figure out who's positive and who's negative. And that leads us to increasing and decreasing intervals. And if we know increasing and decreasing intervals, then we can find maxes and mins, relative maximums and minimums. And remember, we can ask questions that sort of land you at all different spots along that little timeline there. We could just say, hey, find the critical points. We could say, where is the function increasing and decreasing? And we could say, where are the relative maximums and minimums? And then you'd have to do all of it. If you're going to justify, you would say f prime changes either positive to negative or negative to positive, depending on which one you were justifying. And sort of this whole process, or at least this last couple steps of the process, is called the first derivative test, because you're using the first derivative to find those maxes and mins. All right, that was our first derivative stuff. Then we did pretty much the same set of stuff, the same set of steps, the same processes with the second derivative. Set the second derivative equal to 0 or undefined. And this is where the parallels break down a little bit, because there's not a special name for those points. Like, I wish somebody would come up with a name for those points, because then we could make this nice table and everything would fit. I guess the best we can do right now is to say that those are potential points of inflection. Which I guess we could add this to the previous line to kind of continue the parallel thing going on. Those critical points are potential maximums and minimums. But we've got to go further to test to see if they are maximums or minimums, or neither. All right, potential POI that don't have a name, but we're still going to follow the same path. So we'll put our potential points of inflection again on a number line. And then that will tell us concavity intervals. So if f double prime is negative versus positive, concave down versus concave up, And we do that to find the point of inflection. And the justify would be f double prime changes signs. Again, another like slight breakdown in the analogy is that there's not a difference between from plus to minus or minus to plus. There's not a different name for that. For the first derivative, one's a max, one's a min, but changing from one to the other in concavity, there's not special names. It's just, if it changes, it's a point of inflection. And again, we can ask all sorts of different questions in there. Where is the second derivative undefined? Tell me about concavity. Find the points of inflection. That's all kind of on the same day that we learned it and the same process, just different points on the process. All right, then we put the two ideas together, like the combination of a first derivative and second derivative thing. If f prime is 0 and f double prime is positive, let's see, what would that mean? If f prime is 0, think about sketching that. It's like, this is not the thing that we memorize, this is the thing about, you think about what that's telling me, and maybe sketch it. If f prime is 0, what does that mean for the graph of f? First derivative is 0. Horizontal tangent line. Horizontal tangent line. And if the second derivative is positive, what does that mean? Second derivative is positive. It means f prime is increasing. It does mean that. What does it mean for f? F prime is increasing, or if the second derivative is positive, what does that tell me? Concave up. So at the spot where we are concave up and have a flat spot, then we found a relative minimum. Again, you can memorize that combination of things, or you could just kind of sketch it out and see what happens. The other ones like it. If f prime is 0 and f double prime is less than 0, and you kind of go through the same thing. It's we've got a horizontal tangent line, and we're concave up. Whoops, didn't make that perfect. Well, then we found us a relative. Whoops, I did that wrong. It's concave down. I was trying to go too fast. Show your work. Prevent mistakes. F double prime is negative. That means I'm concave down. That means it looks like that, which is a relative max. Using that combination of information is called the second derivative test. So, first derivative test, second derivative test, they both tell you maximums and minimums. First derivative uses only the increasing, decreasing stuff. Second derivative uses concavity stuff. But they lead to the same conclusion, which I feel like is a little misleading, because first derivative test and second derivative test both tell you maximums and minimums, they just get there different ways. All right, EVT, extreme value theorem. As opposed to MVT, mean value theorem. This is the easy one. This is one that people are like, it's so easy, it almost, you forget what it is. If f is continuous, doesn't even have to be differentiable, just continuous, on the closed interval, because continuity always goes with closed. If f is continuous on a closed interval, then there exists an absolute max and min on the interval. So the continuity part ensures that there's not anything crazy like asymptotes or jumps or holes or anything silly going on. However you want to get from A to B, got to be closed circles to make it work. So whatever you do to get there, I should have put a cusp in there, but it doesn't matter. Like there's a max and a min somewhere on that interval, and it might be an endpoint, but that's okay. EDT just guarantees there's a max and a min as long as the function is continuous. Which leads to this reminder: to find absolute max and min, what will we need to check? Check endpoints and critical points. Most people remember to check the critical points, but they forget to check the endpoints. And I guess because critical points, like we just spent 5 minutes talking about critical points leading to maximums and minimums and increasing and decreasing. So that's kind of already in your head. It's just don't forget to also check the endpoints. All right. Lastly, and then we'll do some more off of the review. We like these questions. You will get quite a few of them. Given the graph of f prime, we can find all sorts of things. So there is at least one, I'd have to go back and look, there might be more than one, free response question that uses this. We'll give you a graph of f prime, and we can ask you to find all sorts of things. Where is f increasing or decreasing? We can ask for the relative min and max, min or max, or both, of f. We can ask for the concavity of f. Right, because the slope of f prime tells us f double prime. So we got a graph of f prime. Actually, maybe we should back up a second. If f prime is positive or negative, that tells us things about f. F is increasing or decreasing, and then that leads to maximums and minimums. That's just whether f prime is above the x-axis or below, whether it's positive or negative. The slope of f prime tells us f double prime, which leads to concavity and points of inflection. So I'm promising you will get a free response question where I give you the graph of f prime, and then I don't know what I ask about it, but I could ask a whole bunch of different things. Like if you split all this up, you could make that 1, 2, 3, 4, 5, 6 or 7 questions based only on the graph of f prime. All right, 25 minutes, and that's the entire unit. Let's do a few more from the review.